Hi everyone, I'm Chen. I'm here to present our work on the suitability of LLM-driven agent for dark pattern audits. Dark patterns are interface design that subvert or impair user decision-making. In privacy context, they can push users to disclose more information than necessary. For example, this login flow asks user to authorize more personal data than the login itself requires. Or dark pattern can make privacy choices harder to exercise. Like this consent banner, the accept button is visually dominant, while the decline button is small and low contrast. These examples show that dark pattern can directly affect user privacy. In this work, we analyze dark patterns on a specific setting, what users encounter when they are exercise their privacy right. And given this focus, the next question is, how can we detect dark patterns systematically? Prior work detected dark patterns using methods such as HTML crawling, computer vision, natural language processing, and more recently, the multimodal large language models. However, most of these methods inspect static UI artifact, like a screenshot, an HTML segment, or one isolated UI state. As a result, it can miss patterns that only emerge through user interact with the website. Consider the first case. The instructions for exercising a privacy right are spread across multiple pages. Each page may look fine by itself, but the issue is users have to navigate multiple pages to get the complete information. In the second case, one page says user can submit a request by email, while another page says email is not accepted and the user must use the web form. Again, this contradiction only appears when we compare pages. So the key idea is to find all dark patterns in the exercise of privacy right. We should audit the full user interaction trace rather than only the isolated UI artifact. This leads us to two research questions. First, can LLM-driven agents reliably audit dark patterns, including those emerge across user interactions? And second, what limits constrain this agent during the dark pattern audit? To answer these questions, our basic idea is simple. Can the agent reproduce human judgment and identify the same dark pattern as a human auditor? We study this in the context of CCPA right-to-access workflow. And using CCPA data broker registry, we construct a dataset of 456 data broker websites that are subject to CCPA. We also define a right-to-access interaction sequence to standardize the human and agent auditing trees. The human auditor and agent first visit the data broker website and locate the privacy-related links. Then they open those links and review the right-to-access instructions. And finally, if a web form is available as a submission method, they interact with the web form to review its fields and requirements. Let's work through the detailed design flow. Both human auditor and LLM agent follow the same interaction level auditing procedures. First, they traverse the standardized right-to-access workflow, and at each step, they record evidence, including screenshots, URL, HTML, and UI text. This traverse and record process is repeated until the workflow is complete. And finally, the human auditor and agent map the full interaction trace to a predefined dark pattern taxonomy adopted from the prior work. The human side produces our ground truth labeling. We then compare the agent output against the human ground truth, evaluate both classification and explanation accuracy. Here, I'm zooming in on the agent side design. The agent is implemented by a browser agent browser use, and we use GPT-5 as the underlying model. To make the agent perform interaction level auditing, we prompt it with the audit text and the dark pattern taxonomy. To know how prompt guidance affects user audit performance, we then conduct application study over 4 prompt configuration. First, zero shop. It only includes text and taxonomy. And second, we add role prompting to zero shot with a CCPA auditor role. And third, we add few shot examples for each dark pattern categories. And finally, we add a structured chain of thought to each few shot examples. For each audit, the agent returns a structured JSON output, including dark pattern labels with supporting evidence. It also reports the workflow status, including whether the workflow is blocked from completing. And if the workflow is blocked, the agent selects a predefined failure category and provides supporting evidence. Now, we can answer the research question 1. Can the agent reliably audit dark patterns? We found that prompting significantly improves audit performance. And as shown in the table, the largest gain came from adding few shot example, and the best configuration is few shot plus row plus chain of thought, reaching 86.7% of accuracy. We also found that detection performance depends on the type of dark patterns. The agent performs better on localized or directly observable patterns, such as adding step, visual prominence, because the relevant signals are often visible within a single screen. In contrast, interaction-dependent patterns, where signals is distributed across multiple steps, remain the hardest to detect, such as pattern privacy mazes and hidden information. This leads to research question 2, where we analyze what constrains the agent and why some patterns are more difficult to detect. To answer this, we group the constraint into 3 stages: execution, observation, and reasoning. First, execution. Before agent can detect any dark pattern, it must complete the workflow. And in our run, the agent completes 81% of workflow overall. The common failure came from security barriers, automation instabilities, or interaction level failure, like failing to click a button. Second, observation. Even when the workflow is complete, the agent must surface the relevant signals. One problem is when the signal is low salience, such as hidden links, the agent may not notice or trigger them. It helps explain the low recall rate for hidden information. And the second problem is information loss. The agent may observe the signals, but the signal can later be compressed or lost during the long interaction. This affects interaction-dependent patterns such as privacy maze and conflicting information. Third, reasoning constraint. Sometimes the agent observes the relevant signal, but the judgment itself is ambiguous. For example, to what extent a navigation difficulty counts as a privacy maze? This constraint is different from the first two, as the execution and the observation are the limitation of the current agent implementation. But the reasoning failure came from the interpretive difficulty of the test itself, where human auditor can also struggle with. So to summarize, for research question 1, we found that with test-specific prompting, which is few shot plus row plus chain of thought, the agent can produce strong and evidence-backed judgments for dark pattern audits. And for research question 2, we found agent reliability is still bounded by 3 systematic limits: workflow execution, observation, and reasoning. Overall, our results show that LLM agents are promising, but they are better used as a scalable compliance triage tool. They can autonomously traverse privacy workflow and flag potential dark patterns with structured evidence. And human reviewer can then focus their efforts on borderline cases. Our code and data are available on GitHub. Thank you for listening.